All right, section 4.2 is called Sums and Sigma Notation. And I'm first going to talk about the sigma notation part of this. So sigma notation, if we wanted to find the sum of a bunch of numbers, okay, a bunch of terms, A1 through AN. So all that just means a bunch of different numbers, and it's a convenient way of writing them, A1, A2, A3, all the way up to AN. And the way that we would write that is we would use that large sigma notation. You guys have seen that sigma before, probably fraternities, sororities, things like that, but it's a Greek letter. The value on the bottom, A equal, I'm not even saying the letter, I equal 1 tells you where you start. And the value on top, N, tells you where you stop. And then A with the subscript I tells you what you're adding together. So this actually means A1 plus A2 plus A3. It's adding all these terms together. I is called the index of summation. A sub I is the ith term. It sounds kind of funny to say it that way, but it's the ith term. And then, like I was mentioning before, the upper and lower bounds are n and 1. So it's just a notation that's convenient because it writes it in a condensed form. All right, so the first thing we're going to do is we're just going to work a little bit with this notation. So here's an example. What you see is you see basically an equation right here, right? 3i minus 2. It's an equation in terms of I, and it tells you that the I value starts at 1 and ends at 6. So what we're going to do is we're going to figure out what is the A sub 1 term, the A sub 2 term, and so on. We're going to find each of those terms, and how many of them will there be? 6. There will be 6 of them. And then this notation, this sigma at the beginning, what does that mean? Sum. It means we add them together. Okay? So this is grade school math. We're not doing anything more complicated in this particular step than addition, subtraction, multiplication, division, potentially. Okay? All right, so A sub 1 means I'm going to put the number 1 in where I have an I. So this is 3 times 1 minus 2, which would give me 1. And then I'm going to do the same thing with the number 2. 3 times 2 minus 2, which would give me 4. Good. All right, we've got A sub 3, so 3 times 3 minus 2, which would give me 7. I'll do one more, and then I'll make a note. 3 times 4 minus 2, which would give me 10. Do you notice a pattern? What's happening? Yeah, we're just adding 3 every time. So if you notice the pattern, do I have to really keep putting the numbers in? Couldn't I just use the pattern to tell me what A5 and A6 are? Well, sure. What's A5? 13. And what's A6? 16. Excellent. And then the sigma notation says I'm supposed to add all these values together. So this is supposed to be 1 plus 4 plus 7 plus 10 plus 13 plus 16. And if I add those together, grab your calculator if you want, add them in your head, either way, what do you get? 41? Several of you said it, so that must be working out for us. 41, sound good? Okay, does this notation make sense? Feels a little awkward maybe at first if you haven't seen it before, but all the pieces tell you exactly what to do with it. Is it 51?
Oh, yeah, I didn't see.
Yeah? Okay, we'll fix it. I have 51 written down as well, so it must be 51. 51, all right. Any questions on this one? Okay, so the next thing we're going to do is this we could do. We could do this for every value like this. But if the n is a number that's quite large, that might not be very fun. Agreed? You don't want to do n equal to 100. That doesn't sound like a good plan. Even if there's a pattern, I don't want to do the pattern out to 100. Okay? So what we're going to do next is we're going to talk about some summation formulas. So the summation formulas show us a way to sort of skip the actual finding of every single term and adding it together by doing this all at once. Okay? So there are 5 summation formulas, 3 on this slide, I've got 2 on the next one. And the first couple of them we're going to at least justify why it works, because it's pretty easy to see. The first one, you have this written down, is called sum of constants. So think about what would happen. This is a constant C. It's not got an I in it at all, right? So it means that the first term is C, and the second term is C, and the third term is C, and the fourth term is C. So we're just adding together a whole bunch of C's. Okay? repeatedly adding together the same number has another name. What happens when you add 5 plus 5 plus 5 plus 5 plus 5? Well, multiplication. This is just multiplication for however many terms you have. So this term right here would be equal to c times n. C, the number of c's you have, right? So if you think about it, this is just adding a whole bunch of c's together n times. Well, when I do that, that's n times c, or c times n. So far, so good? Okay. The next one is the letter I, just by itself, just I. So if I were to do this one, this would be like adding 1 plus 2 plus 3 plus 4 plus 5 a whole bunch of times, right? But it just adding one more. This actually comes from a really clever gentleman. His name was Gauss, and he wasn't the first one to discover, but he's the one who's sort of anecdotally remembered for doing this, because he was 6 years old when he did it. So he had a classroom teacher who said, this is not a good classroom teacher moment, by the way, that said, I've got to get some stuff done, got to give the kids something that's productive, but will take them quite a while. You've never had a teacher do that, have you? No, of course not. Teachers shouldn't do that. And so she said something like this: I want you to add up the numbers from 1 to 100. That's what this says. This is exactly what this says, with n equal to 100 on top. So you're supposed to add 1 plus 2 plus 3 all the way up to 100. And if you had a typical 6-year-old, that would take a while. But it wouldn't be a totally unproductive task. I mean, addition is a good concept to learn in first grade, right? Okay. But Gauss was bright, and he took just a couple minutes, and he said, I think the sum is 50-50, like 50-50. And he didn't say I think. He knew it was right. So what he did is something like this. So I'll just show it to you in a nutshell because I think it's quite clever. You don't have to necessarily write this down, but I will go through, what's 98? I'm going to do this with the n equal to 100 at the top, okay? So 99, 100. He noticed something like this. 1, 2, 3, 4, all the way up to 100. If I write those same numbers backwards, okay, so I start over here with 100, 99, 98, and all the way down over here to 3, 2, 1. If I do that and I add these values together, what happens to each one that's vertically on top of each other? What does it become? Right, like so the 1 plus the 100 is 101. 2 plus 99 is 101. And we can keep going, and they're all going to add up that way. Do you guys see that? Got a whole bunch of 101s if I do this. So this becomes 101 plus 101, all the way down here, some more 101s. And the question becomes, how many 101s do I have? Do you know? There's 100 of them because there were originally 100 numbers, not 1,000, 100. There were originally 100 numbers from 1 to 100, right? Okay, well, if you think about this, this becomes the same problem I started with, doesn't it? I'm adding 101 together 100 times, so this becomes 100 times 101. Yeah, hang on a second. We're going to get to that in a second. This is 100 times 101. Okay, but the catch is that when I originally started the problem, I had to add it to itself. So whatever it was, and I'll give it a name, I'll call it S. I added S to itself. So this is actually twice my value, right? This is 2S because I had to add it to myself in order to get the repeating number that's exactly like itself. And so then the last result then is that I divide by 2. So the formula itself with the number 100 in here is 100 times 101 divided by 2. Well, why am I getting the 100 and the 101? What about this did I sort of change than the original problem that I started with? This is what we're looking for, correct? Oops. Well, we let n equal 100 to start with, didn't we? I gave you sort of a specific case example. I didn't do it generally for just n terms. I did it for 100 terms. So this 100 right here was because I let this be 100, but originally it was just n. And so what would 101 have been? N plus 1. Yeah, n plus 1. So the formula itself, the actual formula, okay, so now I'm actually going to give you what the point is. The formula itself is actually n times n plus 1 over 2. And Gauss, as a 6-year-old, did this for the number 100. Would you be impressed? I would, and if I were the teacher, I would probably also be a little bit discouraged because I was intending for that to take quite a while, right? And it didn't. So, and this actually does end up being 5,050, so he was actually correct. Okay, all of that to say that I need to erase this now so I have some more space, right? All right, I'm not going to justify the next couple of them, but they have similar sort of feels to them. We can come up with a pattern of what's going on. When I do I squared, this one actually ends up being n times n plus 1, much like the last one, but then it's also multiplied by 2n plus 1 and divided by the number 6. So this is the sum of the squares. So this is like adding up 1 squared plus 2 squared plus 3 squared plus 4 squared, right? That's what this would be, from 1 up to n. And this is the sum that we would actually get, n times n plus 1 times n 2n plus 1 over 6. Yes, Tristan? Yes, you're going to need to memorize these. Honestly, these two right here are the only ones that really require memorization. The first one's pretty obvious. You probably know that fact. If you forgot it, you could probably stop and think, how did that work again? Oh, yeah. And the last two are quite easy as well. So bear with me for a second. You'll see the last two. All right, this one has c times a sub I. It's a constant times a sub I. We've had a couple of occasions, namely derivatives and limits, where we've had something times a function. Right, we've had a constant times a function. What have we been able to do in both occasions when we had a constant times a function? Well, like when we had, let's say for instance, we had y equals 4 times f of x, and we want y prime. What did we do? What happened with 4? It just stays the same, right? And what did we do with the f of x? We took the derivative. So we did the operation on the part that looked like the variable, and the constant part just stayed the same. And this is true for limits as well when we did limits. It's also true here. So this is actually the same as having the c out in front, and then I equal 1 to n of a sub I. So you can just drag the c, the constant multiplier, out in front and rather ignore it till the end. You can multiply by it at the end, but you can ignore it in the meantime. Okay? You'll see why this is helpful in a moment, I promise. All right, so thinking about our beautiful thoughts about limits and about derivatives, what did we do when we had the sum, and we could likewise put difference here, the sum or the difference of two different variable-like terms? Right, like what did we do when we had, with derivatives, this? And we wanted to find the derivative. What did we do? Right, we just treated each one of them as though I was finding its own individual derivative, and then we combined them with the original sign, either addition or subtraction that was between them. We're going to do the same thing with this one. Instead of having the summation of this compound, thing where we're adding it together, this sum, we're going to separate it, and we're going to have I equal 1 to n of a sub I, plus, and we're going to have a second sum from I equal 1 to n, of b sub I. We're just separating it out, and we're finding the first item, and in this case it's a summation of the first values a sub I, and we're finding the second one, b sub I, and then we'll add the result at the end, just like with derivatives and limits. All right, so let's see how this works in practice, because it's actually quite helpful. All right, the first one says that we're going to go from I equal 1 to 16 of 5i minus 4. And 16 is probably at the point where I don't really want to write 16 of these out, right? And please be careful to follow the directions in each section. See how this says use summation rules? And this one over here, where did it go? So it says to find the sum. This one that says find the sum is intending you to actually, beat it out of you, right? Find each of the 6 individual ones, add them together. Once we get over here and it says summation rules, they are not intending for you to do A1, A2, A3, A4, because it says summation rules. You see the difference? Okay. So the first thing you should notice is that there's subtraction going on here, right? Now I sort of said it, but I didn't write it. This is the same if it's subtraction down here, plus or minus. Okay? So this rule right here is the one we're going to first recognize that we can use. The first thing we can do is we can separate this into two summations. So I equal 1 to 16 of 5i minus the summation from I equal 1 to 16 of 4. Make sense? There's one more property that I could use very directly. So that was property number 5. What other property could I use? For the first one, for the 5i, what would it be? What would I do? Okay. Can I pull the 5 out? Would that be okay? Before we start actually trying to evaluate anything? So this is I equal 1 to 16 of I minus the summation from I equal 1 to 16 of 4. What property was that? Number 4, right? Property number 4, being able to pull it out. This is as broken down as it gets. The 5 in the front is going to stay in the front until I have this summation right here. And I actually have the ability with the rules that I have been working with, been given, to find, to find this value and to find this value using properties 1, 2, and 3. So let's do the first one, the I equal 1 to 16 of I. Which property is that? The second one. That's property number 2. Property number 2 says that I should take the n value. So what is my n value? 16. I should multiply it by what value? 17, exactly one bigger, and divide by 2. This gives me the sum from 1 to 16. Okay? This is property number 1. What am I going to do for the second one, the sum from I equal 1 to 16 of 4? Right, I'm going to multiply 4 times n, and n is 16. And what property is that one? That's property 1, and I actually wrote 2 above 1, and I meant to write 2. Sorry about that. So properties 2 and 1 are happening right there. And at that point, it's just addition and subtraction, right? Yeah. Just grab your calculator, add, subtract, multiply, and divide. Actually, we have all 4 operations there. Look at that. Actually, there's no adding. I'm going to take that back. Subtract, multiply, and divide. Those are the operations. What do we get? 616 is what Christian has. What about you guys over here? Agree? Look good? Okay, any questions on that one? Awesome. Okay, we're going to do another example. Same direction set. Use the summation rules to find or compute the sum. This one looks a little different. In fact, it doesn't really quite look like any of the rules as it's currently written. And it is a product, right? I mean, this is n times n plus 1. Well, I don't have a product rule.
Gonna make much n squared minus n.
Yes. So the first thing to do is exactly what Christian said, is we're going to distribute all of that out. Now this is a little awkward. I've left it this way on purpose, but it is a little awkward because I'm using n in a different way. Do you guys see that? The n in this problem is acting like the I. If it really bothers you, you can change the n's into i's so that it doesn't sort of confuse the notation. But they are going to do that occasionally in their book. They'll use a different letter on the bottom, and they chose to use n on this one. All right, there's something else about this one that's a little weird. Do you know what it is? Look back at the summation rules.
That's a minus instead of plus.
The minus happened in the last problem, though, too. It has a square, but that's okay. We've got I squared. That was property number 3.
It's not divided by n.
No. The property rules themselves didn't have division in them. Say that really loud for me, Kaylee.
It starts at 4.
It starts at n equal 4. Do you guys see that? Right here? What did all the rest of them start at? 1. So this should actually have some sort of difference with it, right? If it's starting at 4 and I'm using properties where I'm starting at 1, weird stuff should be happening. So there is something strange that's going to happen, and it'll happen at the very end. So for the moment, we're going to ignore the fact that it starts at 4, but we're going to sort of mark this and make a note to ourselves that we need to come back to this. We're not going to be done until we've dealt with that part of it at the very end, okay? Okay, so in the meantime, we're going to ignore it, though. All right, so this is a summation. I'll put the parentheses around here just for fun. And we need to find the summation of something that's squared. Well, we have a property for that, and we need to have a summation of something that's just value n, and we have a property for that. But the first property we need to do is we need to separate them. So this is n equal 4 to 140 of n squared minus the summation from n equal 4 to 140 of n. And again, those n's are acting like the i's. If it bothers you, just write them as I. I'm not going to freak out about that. It's really quite okay. All right, so there is a property that says what I do when I have I squared. It's property number, what? 3. What does property number 3 say I should do?
N times n plus 1.
Okay, and let me pause for you just a second, Christian. And the n that you're referring to is going to be the 140, right? Okay, so we're going to take 140 times n plus 1, so that's 140 plus 1, or 141. And then I'm supposed to have 2n, so that's 2 times 140, plus, is it also 1? I think so. All divided by 6. Yes?
Under the second one, is that supposed to be n equals 4 or is it minus?
It is an equals. It just didn't register when I made the mark, probably. Thank you. Okay, so this piece comes from here. Now we have minus. Summation of n.
140.
Okay, so again, this is property number which one? 2. This is property number 2. It should say I take the number at the top, the 140, times 141, and divide by 2. But of course, this is actually finding the values as we go from n equal 1 and up, isn't it? So we're going to have to fix that in a moment here, and in this step we're going to have to write something differently, because in this step it's not written right at this moment. We're going to have to put something at the end here. Let's actually just find the values themselves for the moment, though. Just do the first one, okay? Just this piece right here before you subtract. Find out what that number is for me for a moment.
This one?
Mm-hmm.
It's 924497.
Okay, someone else find the second one for me. Right here.
9070.
Yes, Christian, it is. But you're the same person. Okay, and of course we're going to subtract these, so let's go ahead and do that just for fun. Well, not just for fun, we're going to need it anyway, so let's just do it. What do you get when you subtract those two? 9-1. What do you have, Kaylee? What'd you have?
91462.
Okay, is that what you had too, Tristan? Excellent. Okay. Now, the problem is, of course, that this would be if we had n equal to 1 up to the value 140, and we don't. We only started at n equal to 4. So in particular, what this notation is supposed to be meaning is that I'm supposed to start at A4, A5, A6, and go up to A140. So what do I not have? A1 through A3. So right now, what's missing right here is that I do not have A1, A2, and A3. But the summation value that I just got presumes that they're in there. So I need to take them out, right? I shouldn't have A1, A2, and A3 in this sum. So back up here where I did this piece right here, I need to take out A1, A2, and A3. How can I do that? What do I need to do? I need to find the value of A1, and find the value of A2, and find the value of A3. And you know how to do that. How do I find the value of A1? You just put in the number 1. All right, so, and you can put it in from the original function that was given, the original terms that was given, n times n minus 1. So if I put in the number 1, I'll do this over here on the side so that I've got enough space. A1 would be 1 times 1 minus 1, which would be 0. So A1 is 0, so that doesn't actually affect anything. A2 would be 2 times 2 minus 1, which would be 2. And A3 would be 3 times 3 minus 1, which would be 6. So the numbers over here that I'm supposed to be taking off are actually 0, 2, and 6. And I'm writing the 0 there just to remind you. I mean, it's one of the values. It doesn't affect it, but it is one of my values. So I should be taking off 8 from the sum that I just had. So what is 914620 minus 8? $914,612. $914,612. This is probably the part that trips people up, is because it's sort of sneaky. I mean, it's not, but it's just, you have to be aware of what's happening. Most of the time they start at n equal to 1, but sometimes they don't. So that's why I actually put this star to remind ourselves at the very beginning so that we didn't forget it when we got to the end. Also, notice what I did. When we go back upward, the first place that the values actually need to be taken out is this step right here. So if you leave all of this and you didn't put it here, didn't put it here, and then put minus 8 at the end, that wouldn't be quite right either, right? Each step is supposed to be equal to the one before. The only way this step here is equal to the step before is if it shows that I need to take those 3 values out. So that's the point when I need to have minus A1, minus A2, minus A3.